so thank you for the introduction. I'm going to talk about a work jointly done with Job Briet and Sandra Gerling, who are both in the audience. And this work does a relationship between two concepts, one from function analysis, which are the Grothendieck inequalities, another from quantum quartic complexity, which is the polynomial method. And what we have shown is that the Grothendieck inequalities characterize converses to the polynomial method. So the first thing that we are going to do in this talk is introducing these two concepts. Then we're going to state our results. And finally, we are going to talk a bit about the tools that we have used to prove them. The first thing is saying what is the Grothendieck inequality. The Grothendieck inequality is an inequality for square matrices. For square matrices, you can define a binomial form in a natural way, in a canonical way. And if you fit that binomial form with real numbers, you get the infinity norm as the norm of this binomial form. And if you fit that binomial form with matrices of any dimension, then you get the completely bounded norm. And of course, by this definition of the completely bounded norm, it's clear that the completely bounded norm is bigger than the infinity norm, because if you fix here the dimension of the matrices to be 1, you recover from the completely bounded norm the infinity norm. But here, this is allowed to be an integer, so this is only going to be bigger than this. Okay, so what is interesting is...
Why CB?
CB? Oh, okay, it's from completely bounded.
Completely bounded.
Yeah, completely bounded. It's a bit,
all right, that's fine, don't worry.
Sorry, and I think you might have said this, but I missed it. The two lines are the operator norm?
Okay, I didn't say it, so thank you.
Oh, never mind.
Yeah, here the lines are the absolute value, and here the two lines are the operator norm, because at the end of the day, if you take the entries of the matrix and you multiply them by other two matrices and you sum everything, then you get another matrix that is going to be a square matrix, and then you can define the operator norm, and that is the norm that we are going to get.
Sorry, what's the product in the second line? I mean, you have an
Here.
Yeah. Okay. Sorry, AIBJ is a matrix product among D by D matrices.
Yes.
Indexed by I and J.
Yeah, this is a matrix, and this is a number, because these are the entries of the matrix. Maybe, yeah, this notation is not super good because I'm calling it.
Yeah, you should have called them big X and big Y, to be honest.
Yeah.
Is AI and BJ or anything to do with A?
No. That is what. There is notational mistake. Okay.
So from in the first line, it's not exactly the usual operator norm, right? Because then I would have like norm of X and Y less or equal to 1.
Yes, but okay, but now is the usual operator norm when you regard the initial space as L infinity,
right?
Because if every entry of the X is bounded by 1, this means that the infinity norm of X is almost 1.
It's infinity to infinity.
Sorry again.
Okay, I'm with.
Why do you need a double bar at the there? Because it seems to be a real number, or could be a
No, these are matrices.
Again?
These are matrices. Of
Yeah, sure. Okay, I'm sorry.
Well, so then you're obliged to tell us what norm that is of D by D matrices.
Yeah, the operator norm.
The regular operator norm. Yeah.
So how do we ready to go?
Everyone's happy with the norm. So let's go.
Okay. So the interesting thing is, okay, we already have said that the infinity norm is at most the completely bounded norm. But what is interesting is that these two norms are equivalent, and this is known as the Grothendieck inequality. That was something proved by Grothendieck 70 years ago. And he showed that there exists a constant such that the completely bounded norm can be upper bounded by the infinity norm times that constant. And this is interesting in so many ways. And this the precise value of the best constant that are here is unknown. The Grothendieck constant is unknown. We have good upper and lower bounds, but it has been an open problem to determine the exact value of the Grothendieck constant for 70 years. But just to say, as an application of this Grothendieck inequality, there are many mathematics, but there is also a very famous one in quantum information theory, which is the zero-sum bound. In the 80s, zero-sum showed that if you get an XOR game of 2 players, you can define a matrix such that the infinity of that matrix is the classical bias, and the completely whether or not of that matrix is a quantum bias. So at the end of the day, what Aaronson did was translating the Grothendieck inequality to the language of quantum information theory, and that is what is known as a Aaronson band, which is important because it's telling you that the quantum bias cannot be much bigger than the classical bias. So for XOR games of 2 players, the classical and the quantum correlations can do almost the same. Okay.
Sorry again. If you want the third line from the bottom to define the constant, then I suppose you mean it is the smallest number. So that
Yes,
is one.
that is the best constant, the smallest one.
So I remember Grothendieck inequality relating the norm infinity and the sum of A and J in a product of unit vectors.
Yeah. Okay, that is an equivalent way of writing this expression because here, if you remember that the operator norm of a matrix is the supremum when you inner product the matrix with one vector that is normalized here, another vector that is normalized here, then you recover that expression. Yeah, and that is equivalent. I just wanted to use the expression that is less usual. The usual one is that the one that you said because that is more similar to this one. Yeah.
Similar, huh? It's just going from scalar to vectors.
Yeah, and it's also going to be more useful a bit later to have this idea of the growth of the completed bounded norm in mind. Okay, so this is a brief summary of what the Grothendieck inequality for matrices is. But you can also wonder if the Grothendieck inequality is true for higher degree tensors, because at the end of the day, matrices are 2 tensors, and you can define these norms, the infinity norm and completed bounded norm, if you have a tensor of higher degree. For example, if you have a 3 tensor, you can also define the infinity norm in a very natural way. But now, instead of taking a binomial form defined by a matrix, you take the trinomial form defined by the 3 tensor, and you do the same with the completed bounded norm. And of course, the infinity norm defined this way is going to be at most the completed bounded norm because of the same reason. But what is no longer true is that these 2 norms are equivalent. Now, there is no constant such that allows us to upper bound the completed bounded norm by the product of the constant times the infinity norm. This can be regarded as a consequence of a few works, for example, a work of Pérez García, Wolf, Palazuelos, Villanueva, and Junge that was done in 2008. And there they saw that there is unbounded violations of very inequalities when you have 3 players. Also, this can be regarded as a consequence of a work of Job Priet and Carlos Palazuelos of 2019 that we are going to use a bit later. Okay, so the takeaway message so far is that the Grothendieck inequality is something that relates the infinity norm and the completed bounded norm, saying that they are equivalent when you're working with matrices, but that inequality is no longer true when you are working with tensors with more than 2 entries. Yeah.
Is there any upper bound you could put if you let k depend on n? So like for every n, it's like a most maybe like square root n. Oh, do you know the value or? There's
Okay, so if we are all happy, now we can go to the quantum information part of the introduction, and we are going to talk about quantum query complexity of Boolean functions, which are functions defined in the Boolean hypercube that also take Boolean values. So quantum query complexity cares about how difficult it is to compute f of x on every x. And we are not going to be able to read the whole input because otherwise that task would be trivial. What we are going to do is just trying to obtain as few information about the input as possible. And this information about the input in the quantum world is obtained through an oracle gate that encodes the information about the input. So we are going to use, we want to use this oracle gate that contains information about the input as few times as possible. And despite using the oracle gate as few times as possible, we want to output something that is very close in probability to f of x. So in precise terms, a quantum query algorithm is an alternation of fixed unitaries and these oracle gates, these queries, and at the end we measure. The measurement is going to be 1 if we measure the qubit 1, and if we measure the qubit 0, the output is going to be -1. So at the end of the day, a query quantum algorithm is an algorithm that uses t times this oracle gate, and at the end we have a measurement. So at the end of the day, for every x, a quantum query algorithm is going to determine a random variable that is going to be binary. It's only going to take values -1 and 1. And as a binary variable is going to be determined by the expectation of the variable, and as the values are -1 and 1, the expectation is going to be between -1 and 1. So what we are going to understand in this talk as the output of a quantum Fourier algorithm is this family of expectations of random variables determined this way. So now we are ready to define. Yeah.
What's the meaning of AQ and W? A for
Okay,
instead of for work, AQ for
Yeah,
quantum,
this is like kind of the special qubit that is, yeah, maybe the ancilla qubit, yeah. But the thing is that, okay, this oracle gate is the oracle gate is defined in the following way. You take a bit string, you encode it into a unitary as the diagonal of that unitary, and you say that that unitary is a diagonal matrix with that bit string the unitary, and then you make a control version of that unitary. And the control bit is this ancilla, okay? And this is somehow encoding the subject of the input. And this is the workspace, which is some kind of extra dimensions that you can use to your algorithm.
I still have no clue what you mean. The input here is X actually. It's OX. OX is the input. You want to decide something about OX, right?
Yes.
So why don't you just put all zeros in input?
Why
Why not just all zeros as input? Zeros.
Labels for the
Use
registers.
zero could take care of it.
Oh,
No, they're labels for the registers. They're not initial states. The A is for auxiliary that you use to control. The query Q is for the query, and W is the work register. They just indicate.
But if you just had a bunch of zeros, it would make no difference.
Well, you can initialize all these registers to the all zero state.
All right.
So now we are ready to define quantum query complexity. So given a Boolean function and non-negative epsilon, the epsilon approximate quantum query complexity of the Boolean function is the minimum number of queries that we have to make in order to approximate the Boolean function up to an error 2 epsilon. And the 2 is there for historical reasons. But now there is another question, which is how are these expectations? Well, what can we say about these expectations? And maybe the first people wondering about this were Billis, Burman, Cliff Mosk, and De Wolf, who more than 20 years ago proved the polynomial method, which states that if you have a quantum query algorithm that does the queries, then the output of the quantum query algorithm is going to be a polynomial that is going to be bounded, which means that it's going to take values between -1 and 1. We have already explained why. And the degree of that polynomial is going to be at most 2t, at most 2 times the number of queries. So now if you introduce another measure of complexity, which is the approximate degree, and is defined in the same way as the quantum query complexity, but now instead of approximating the Boolean function with quantum query algorithms, we will approximate it with bounded polynomials, then you can relate these two measures of complexity. You can lower bound the quantum query complexity by the approximate degree. And this is nice because now if we want to prove that something is hard to do in a quantum computer, we can forget about the quantum part and just prove that that thing is difficult to approximate with polynomials. And quantum algorithms are maybe a bit more difficult than polynomials, which are objects that are very well understood in mathematics. So this is another result that also has a few applications. For example, in the original paper, the author showed that Grover was optimal using this polynomial method, and also other things have been proved. In fact, many more things have been proved using the polynomial method, but just to name a few, collision finding and alignment distribution algorithms that we know nowadays are known to be optimal thanks to the polynomial method. This is a work of Aaronson and C. 2009. So we have this result, which is nice, it's useful, but it's also a mathematical statement. So as a mathematical statement that has one implication, I can also wonder if the other implication is true. The implication from the right to the left true. Is there a pure converse to the polynomial method? And the answer is no, and this can be regarded as a consequence of a work of Ambanis in 2004. And the non-existence of the pure converse means that it's not true that for every bounded P that has degree at most 2t, there exists a t-query quantum algorithm that outputs exactly the P. And now what I'm going to do is introducing a quantity that is not so mentioned in the literature, but is a very natural quantity to define. And this is the quantity that is going to allow us to state our results in a more compact way. And also is the quantity that we are going to be able to analyze with our techniques. This quantity is given a polynomial P and a made of queries T is the error PT. And the error PT is defined as the minimum error that you can make when approximating P using T-query quantum algorithms. So now with this definition in mind, we can restate the fact of Ambanis in this way. Say that it is not true that for every bounded polynomial of degree and most 2t, the error PT is 0. This is simply another way of saying that there is no pure converse for the polynomial method. But as this slide is titled possible converses to the polynomial method, maybe there is another way of having a statement like this that is not exactly this because it's false, but a bit weaker, but true. So this is something that some people have wondered about.
Can you go back to the definition of
Yeah.
QE? It's like you're going very fast. Can you go back?
I think so.
Where you were back, before that, yeah, Q,
Q,
epsilon, exactly. Can we save this somewhere? That's the ultimate disadvantage of Weber's line.
Yeah.
Because usually okay, the factor 2 is there because usually you define the quantum epsilon query complexity as the minimum number of queries that you have to make in order to approximate your function in probability with an error epsilon. And this translates into an expectation error of 2 epsilon. Okay.
Okay, so you have this. Then on the next slide, you define the approximate degree,
Yes.
which is now polynomial. You require the existence of polynomial of degree above t, which approximates f of the error to epsilon. Okay, and then there's a relation between the two.
Yes.
Polynomial method. Okay.
Good.
Yes, and now you define yet another quantity, this epsilon.
Yeah, this is the last definition.
It's fine, but they all look very similar, and I
Yeah,
guess
yeah,
they're crucially different. So that's why I'm trying to.
Yeah. Here we don't. In the previous ones, what we did was fixing epsilon and f and try to find the minimum number of queries. Here we fix the number of queries and the polynomial, the thing to approximate.
So how is this different from what you wrote before?
This,
Finding the smallest epsilon.
yeah, the smallest error that you can make when approximating a
Before
polynomial.
it's the smallest number of queries. And you
Yes.
fix t and you.
Yes. Okay.
Yeah. Okay.
So I don't know
With
what
parameters.
So maybe now, okay, so I just said that there is no pure coverage for the polynomial method, and I have stated this result in this way. So the next thing to do is wondering about which is a possible coverage for the polynomial method, and thanks to a result of Aaronson, Bainis, Iraitz, Kokainis, and Smortrov.
One question, because it's so for any polynomial, even though I allow myself to do like infinite amount of queries, I cannot approximate it. Like this
Yeah.
EPT 0.
EPT is 0 if you have, for example, t equal to.
But can I not just query my entire
Yeah.
string and then calculate my
Yeah,
polynomial on
that is
the?
why EPT is 0. When t is n.
The fact is, talking about the fact.
Yeah, so somehow this is in the, like, the t here is in the. I get a bit confused because the t is a parameter of your function, right? This EPT. So
It's not false for every polynomial.
I think the first line would be much more easy to interpret if it were there exists a p rather than for all p. I think with the for all p, it's like the logic is basically totally messed up. Like, this doesn't really make sense.
Not for all.
Yeah, it's not for all, yeah.
Yeah, so
There
there exists.
exists.
Yeah.
There's
Yeah,
that
sorry, that
non-
makes more sense.
Oh, okay.
Yeah, sorry. So
Oh,
not for all
okay.
p, you can say that the error pt is 0.
There is at least
I
one.
guess it is actually kind of a logically not correct because it should be not for all p and also the not in the implication.
It should be for all p.
Take a double
I don't know how you define your logical symbols.
But I mean, like,
I don't know.
what the hell is going on?
just take p as 0.
Yeah, maybe we can forget about this and simply say that it's not true that if p is bounded and of degree at most to t, then this does not imply this.
So there is a p for which it's not true.
Yeah.
Yes, very good. I'm happy.
I'm not. Maybe I'm the only one who cannot follow, but like, what's this fact saying?
I think you have to either remove the, like put it's not for all, and then the implication is positive instead of with the line.
Well, you had a different version before, no? Can you maybe go back
Maybe
to?
this version is more.
Yeah.
clear, Because in that new version, you have to understand what is the error PT. But here, what I want to say is that there is a polynomial that is bounded and of degree at most 2t that cannot be approximated exactly, that cannot be described exactly by a t-query quantum value. So,
For all signs, you just go.
yeah, forget about this. I cannot erase it.
Yeah.
Okay.
And what is this? Does it matter? Is
I
it
mean,
easy to
it
say
matters
what
in the
this
sense
polynomial
that,
is?
yeah, it's conceptually important because this means that this result is not an if and only if. That what you cannot put with quantum query algorithms is not only complete, is not all bounded polynomials.
Yes.
But that was true.
The question was like this polynomial there that exists. Is it easy to specify? Or
There are many polynomials. We will see a few in a few moments. We will have stronger results than this. Okay, so the thing I wanted to say is that, okay, we don't have a pure converse for the polynomial method, but maybe we have another kind of converses. And these kind of converses are, for example, one that was proved by Aaronson and Baines, Iraitz-Kokanis and Smortros in 2015, where they showed that there is a multiplicative converse for polynomials of degree 2. This means that there exists a constant between 0 and 1 such that for every p that is bounded and of degree at most 2, the error CP1 is 0, which means that you cannot put exactly CP with one quantum query if you multiply the p by a constant. So we are introducing a multiplicative error to the p, and then we get a converse for the polynomial method. So this is why we get a multiplicative converse for polynomials of degree.
What was this proof constructive in the sense that it would give the constant?
Yes, you can give a constant, you can give an upper bound on the constant, and this constant is related to the Grothendieck constant, because what they use to prove this is the Grothendieck inequality.
All right.
And yeah, so that is the reason why they could not extend the result to higher degree, because the Grothendieck inequality, as I have said at the beginning, is something that is true for matrices, for polynomials of degree 2, but is not true for higher degree. So they could not extend with that technique this result to higher degree. Okay, but what is nice is that these multiplicative converse that have a multiplicative error, which might not be supernatural.
Sorry, can you go back one slide? Is there some way to kind of rewrite this and get the C out of the C times P, but get it into the error?
Very good question. Next slide, I'm going to explain that. So yes, that is the weird thing is that you have the C inside of the P, and that is not super usual in quantum query complexity, because you have usually not multiplicative errors, but additive errors. And that is what I'm going to explain now, is that this multiplicative converse implies an additive converse. So this means that if you take the polynomial, you compare it with the quantum query algorithm that does one query and output C times P, then the difference of these two things are going to be bounded by 1 minus C. And as C was between 0 and 1, this is something that is controlled by 1. So this is saying that you have an additive converse, because for every P that is bounded and of degree at most 2, then the error P1 is at most 1 minus C, which is something non-trivial because it's more than 1. If this was 1, this would be a trivial result, because you can always output something that is zero in expectation, and as you are going to try to approximate something that is bounded, you are always going to make an error that is at most 1. So the interesting thing is having a converse that has an additive error, but is controlled by something that is at most smaller than 1. Okay, and why this is interesting? Because now what we can do is establish a comparison and equivalence between quantum query complexity 1 and approximate degree 2. What I mean by this is that we knew, thanks to the polynomial method, that quantum query complexity 1 for a given epsilon implies that the epsilon approximate degree of that function is at most 2. That is simply the polynomial method. And now what we know, thanks to the result of Aaronson and Baines and co-authors, is that the epsilon, if you pick epsilon small enough and you have that the epsilon approximate degree of the Boolean function is at most 2, then for another epsilon a bit bigger, the approximate query complexity is going to be at most 1. And why is that? Because if you pick f and then you take the polynomial that is bounded of degree at most 2 that approximates f very well because this epsilon is small. And then from that polynomial, you define the one query quantum algorithm of here that makes an error of a node 1 minus c. Then that polynomial is that quantum query algorithm that only does one query is going to approximate very well your Boolean function. So for this error, the quantum query complexity is going to be at most 1 because you have a one query quantum algorithm that approximates your f with this error.
Constant depend on f.
No. That is the interesting thing, that this constant does not depend on f somehow. Because this is for every f. That is somehow why we want this constant not to depend on it.
Same figure for total Boolean functions, but I guess it's also true and also more interesting for partial Boolean functions.
Yeah, this is true for total and Boolean partial. Sorry, I was just talking in the intro about total Boolean functions just to be simple, but this is also true for partial.
It's important to allow that because we know that if you have a total Boolean function that depends on n variables, then its approximate degree is already like log n.
Yeah.
Which means that if you restrict the approximate degree to the at most 2, you're basically restricting the number of variables on which your function.
This is
So that's why it's important to allow partial Boolean functions.
That I have not thought about that, but thank you for motivating the talk. Any more questions? No? Okay. So as I said, these techniques of Aaronson and co-authors do not extend to higher degree. So they wondered about what happens for polynomials of higher degree.
With from milligrams free.
Okay, because
Sorry.
as you are quantum query complexity T implies polynomial degree 2T. Okay. So the next step would be what happens with polynomials of degree 4. Okay, so the way that we interpret this question is that is it true that there is an additive converse for polynomials of degree 4? Is it true that there is an epsilon between 0 and 1, important that is smaller than 1, such that for every p that is bounded of degree at most 4, the error p2 is at most epsilon? Do we have a controlled converse to this kind of polynomials that are bounded of degree 4? And the answer is no, and that is the first of our results. And we have proved that using this error p t thing. In particular, what we have shown is that if we consider the bounded block multilinear forms of degree 4, which I'm going to explain later exactly what they are, but they can be regarded so far from now as bounded polynomials of degree 4. If we take the supremum of the error needed to approximate those polynomials with two quantum queries, then we are going to get one, and that is the converse, because we have said this error 1 is trivial to attain. So this means that there is no additive converse for polynomials of degree 4. Okay, also using the same techniques, what we have done is wondering about what happens for binary forms for bounded polynomials of degree 2, and taking the supremum in these binary forms that are bounded, we get that the best error that allows you to approximate any binary form with one quantum query is 1 minus 1 over the Grothendieck constant. And this is nice because now we have characterized the Grothendieck constant, which is unknown and is a big open problem to determine it using quantum query algorithms of one query. So maybe this opens a new route to determine this mysterious constant. Okay.
How does this relate with your C of the previous slide? This 1 minus C, are you showing that C is 1 minus over kg now?
Yeah, the C of the previous slide that Aaronson and co-authors obtained was 1 over the Grothendieck constant. So Aaronson and co-authors kind of proved the upper bound. Yeah, the upper bound of this result. But we kind of saw that this is not only an upper bound, but also a lower bound. So we saw that the techniques of Aaronson and co-authors are tight in some sense.
So you could also have put 1 over kg in the previous slide.
Yes.
No.
For binary forms. Yeah.
For linear forms.
For binary forms. This is only for binary forms. The Aaronson and co-authors, what their C is more universal because their C is valid for any polynomial of degree 2 that is bounded. But what they did is reduce in that case of bounded polynomials of degree 2 to the case of bounded linear forms, and then they apply the Grothendieck inequality. So this C is the C that they obtained for bounded linear forms, but not in general.
Otherwise, it would be bigger.
Yeah.
We know it would be bigger, or it might be bigger.
Yeah, that I don't know.
Okay.
They have to use a bigger C, but I don't know if it has to be.
So here, this is really nested optimization. We have a supremum over set V2, and then inside there's an infimum over the one query quantum. So it's sort of like it characterizes this Grothendieck constant, but the optimization is always in the weird sense.
You say that this is a weird set.
Well, I don't know what it is yet. To me, it is
Yeah.
weird.
So it's easy. This is simply a linear form that is bounded in infinity. I think that this is not.
Oh, I thought this was this block.
Yeah, but which specified when t is equal to 2, when the e is 2, is simply linear forms that are bounded. So that is not super good, right? Okay. So also I want to say that what we have used to prove these things is the relationship of quantum algorithms with completely bounded polynomials, and that relationship was established 5 years ago by Aaronson, Briet, and Palazuelos, and it was an important result because it fully characterized quantum algorithms. But the problem was that that characterization was done through the completely bounded norm, and that completely bounded norm is a bit complicated to understand. And what we have done here as a byproduct to prove these two things is simplifying the expressions of the completely bounded norm of tensors and polynomials. Okay, so this is what we have done in our work. So if you have any question about the results, please go ahead.
What's the star? CB star.
Oh, yeah. Sorry, I didn't say anything about this, but we also gave formulas to compute the dual norms of these norms. Okay, the dual versions. The star means dual. Okay, if you say a norm star is the dual version of the norm.
Can you say anything about the piece which achieves the maximum? I assume this is a compact set, or I don't know exactly, but can you say like something about like a polynomial where you get the EP2 equals 1 or the EP1 equals 1 minus 1 over kg? Or is this just
No, because you have to go to infinite. I mean, it's believed that you have to go to infinite number of variables to attain the Grothendieck constant. So you kind of need to go to infinite number of variables.
Oh, I see. So this is the space. Oh, for all n, I realize.
Yeah,
So this is not the space for a fixed n. This is the space over all n.
Yeah. I'm not writing the end
see.
just to be.
No, I okay. All right. But you can't even say something about like a sequence which might converge or something like that.
There is sequences of things that converge the quotient of their norms converts to the polynomial to the Grothendieck constant, but I don't know exactly if that implies that the error of that's probably.
I want to wait to see what you did, and then maybe I can ask my question.
But yes, I think that yes, you can say something, but it's not super useful.
Okay.
I also want to explain why dual norms useful, or like how they're using it.
Okay, they are going to appear on. I said that we are going to give analysis of this quantity, and this analysis is going to use these dual norms. So at the end of the day, we are going to reach an expression for this quantity that depends on the dual norms. So if you have an expression of this quantity that we can analyze, we don't need to be able to compute these norms. But if you give an expression for this quantity, it's nice also to explain how you can compute it. Nothing else? Okay, so now I'm going to introduce the completely bounded polynomials, and first of all, I have to speak about notation. I am going to say that a T form is a polynomial that is homogeneous of degree T, and for every of these polynomials, there are many tensors that are associated in this way to the polynomial, but only one of them is symmetric. What I mean by a tensor being symmetric, this symmetric tensor, I'm going to call it TP, is the following. First of all, I'm going to introduce what is the permuted version of a tensor. If you have an element of the symmetric T group, a permutation of T elements.
I'm sorry. What's a form?
A form is a polynomial that is homogeneous.
Again?
Homogeneous polynomial equals form.
Oh, okay. Form.
Yeah. Okay. Okay, so I'm going to define the permuted version of a tensor. So if you have a permutation of T elements and you have a T tensor, then you can define the permuted version of the tensor as the tensor that is also of T entries that has the same entries as the original one, but now permuted according to the permutation. Okay, so TP is going to be special because it's going to be symmetric, which means that TP is going to be invariant on the permutations. And there is only one T such that is associated to P and is symmetric.
So one more notational thing. So you write X and then this the parentheses I1. No, yeah, in the first formula. You're there, yeah. Is this the I first variable?
Yeah, this I1 is a number, and this would be the X, the I1 entry of X. Yeah, but I wanted to. Yeah, maybe I was
Not the I1's variable of X, X1 to Xn.
And sorry, I want through IT all distinct,
How does this correspond?
Not necessarily.
not necessarily distinct. Okay, fine.
Yeah, that is also one of the reasons why you can have many decompositions of the polynomial with this kind of this.
So you could also write this Ij as subscript of X.
Yeah, but it's going to be a bit more useful to see it as this because I'm going to use subscript in the next slide for in the next slide for something a bit different. Okay.
But you use it up there, no?
Oh, okay. Okay, this is a mistake.
There you did write it as
Okay. Sorry about this.
But just to point you to these variables in you, that's why there are many options.
Yeah, that is the point. Yeah, so this means somehow that you have so many non-commutative polynomials associated to the same commutative polynomial. Are you okay, Martin?
Yeah.
Okay.
We'll go back, please. Go back,
Okay.
Go back,
So
please. So I'm trying to understand it. G of X is column equal means by definition.
yeah, this is the definition. I'm
So
going to use
G of
that.
X equals P of X.
Yes, I mean, this is how I define the evaluation of a tensor in bit string.
What I mean, how can a tensor be equal to polynomial? What does it mean?
This is the evaluation of a tensor on a bit string. And what I'm saying is that given a polynomial, there are many tensors, such that when you evaluate the polynomial on a bit string, the tensor.
I think I assume that the reason we're doing this over real polynomials and not complex polynomials.
It does not matter.
It doesn't matter.
Yeah, at the end of the day, it doesn't really matter because, of course, it's more natural to do it with real polynomials because when you do quantum, you usually use real numbers, but at the end of the day, you can do quantum algorithms only using real numbers. This,
No higher. No.
oh, the degree, yeah. This is the usual notation to say that you have a polynomial and the equality is that the degree is exactly.
In relation to Quinton's question, doesn't the value of the Grothendieck constant change if you go from the reals to the complexes?
Yeah, it changes. But the value that is relevant here is a real value. That is, there is, yeah, even though if you even work with quantum algorithms that are complex, as you can reduce them to real numbers, the Grothendieck constant that we're caring about is the real Grothendieck constant.
Is it very easy to see that you can assume that you're dealing with real polynomials? Is there no factor 2 involved?
Yeah, you have to change the dimension of your workspace, and that's it. Somehow you have to duplicate it. It's not as easy as that, but there is a few papers that say that you can somehow work with real numbers in many ways in quantum. Not in every way, but in this case, yes. Engineers? Okay, so remember that for a T form, there are many tensors associated to that T form. To that P, given a T form that is P, there are so many tensors associated to P, but only one is symmetric. Okay, so now we are ready to define the completely bounded norm of tensors and of polynomials of T forms. And given a T tensor, the completely bounded norm is defined as I stated in the beginning, in the introduction. You take the tensor, you define a T multilinear form, and you fit that multilinear form with matrices that are contractions, then you take the operator norm of the resulting matrix, and then you take the supreme. Okay, this matrix can be of any dimension. I didn't write it just to save a bit of notation, and I have already written that at the introduction. So this is the complete wonder norm of a tensor. It's not super difficult to understand the definition, but for the complete wonder norm of a polynomial, it's a bit more complicated. Okay. Okay, S is, yeah, let's go, is an index, is a subindex that goes from 1 to t. That is why I wanted to use the parentheses inside the variables before.
So it is also of the dimension of
Yeah.
the indices, right?
Can you parse it again? So what are the variables? A1 up to how? So now I'm lost between the A1 and the I1 and IT. So how many matrices do you have?
You have t times n, because for every of these sequences, you have n and you have t sequences.
Also, you have a variable, you have n times t matrices.
Yes.
Okay. Of any size.
Of any size, yeah, of square matrices of any size. Yes. Okay, is this okay? Okay, so the next thing is going to be the definition of the complete wonder norm of a polynomial of a T-form. And this is a bit complicated.
So I don't know if we should go, but like, can you go back? Because this should also map to the axis you had before. So this n times t on the previous slide, this should, but there you had n axis.
Yeah. Because here you are considering the polynomial, not the multilinear form. If you have a multilinear form, if you evaluate here, if you take a1 equal to a2 equal to at, then that from the multilinear form defines a polynomial. And here we are talking about polynomials, but tensors can be also regarded as multilinear forms. And that is how you define the complete wonder norm. You regard the tensor as a multilinear form. Okay, so it's not the same. Here we regard the thing as a multilinear form, and here we regard it as a commutative polynomial. Okay?
Yeah.
Okay. This is the definition of the complete wonder norm of a tensor, and now we are going to define the complete wonder norm of a polynomial. So, given a polynomial, you take the symmetric tensor associated with that polynomial, and you take all the compositions of the tensor in this way. For every sigma, you take a tensor and you sum the permuted version of that tensor, and you sum overall the symmetric group, and then you should get the symmetric tensor. Among all these families of T sigmas, you take the sum of the complete wonder norm, and the infimum of these sums is going to be the complete wonder norm of the polynomial. This looks complicated. I had to make an effort even to say it. So now I'm going to show how these two things can be simplified. The first
definition, like, because you multiply these matrices in a specific order, like if you permute into the tensor, does the norm change?
Yes.
Okay.
It can change.
TP, are you just saying TP is a representation of P? Is that what T sub P means there?
Yeah, this would be.
So you're saying if I
one
yeah.
that is symmetric. The symmetric one.
Oh, the only symmetric. Oh, I see.
Yeah, but so TP is well defined. You have P, so you have TP, which is full symmetric tensor.
Yeah.
Okay, and then what is T? I mean, I know TP, but then you define it as a sum of T sigma, which means that you have a T. I have T sigma, but what is T?
And T sub sigma is another tensor. So you have a sequence of T sigmas.
Oh, these are
You
very,
get to
so
choose
again,
them. So
variables.
you have an infimum over decompositions of TP in terms of T sigmas. And each of them
You look at all possible decompositions of TP, but there was easier definition.
Did you take a construct of T sigma, you take a random T, and then you start permuting on the indices?
So take a matrix, right?
Yeah.
Take a symmetric matrix. You can decompose it as a sum of different matrices. Right. So upper triangle one and lower triangle one,
Yeah.
zero something, and you add it. Right? You choose where you.
And so to be clear, the T sigma or T sub sigma does not have to be symmetric.
So, okay, so
No, there is no rule. It can be any T-tensor, and you only care about finding families of T-tensor indexed by the elements of the permutation group such that they satisfy this decomposition of the symmetric tensor associated with the polynomial. It's complicated, yeah, but we are going to simplify it. So
it is very messy. Right? So you have a T form P, symmetric polynomial P. Associated with that is a T sub P.
yes, the symmetric one.
The infimum in that expression is taken over all the possible ways in which you can write that T sub P,
Yeah.
totally symmetric, as a sum of arbitrary tensors, not necessarily totally symmetric,
Yes.
which looks horrendously messy.
Thank you. Thank you. I love this motivation. I love this motivation because now this is going to be more, yeah, the result that we are going to state now is going to be better motivated. So any more questions to motivate the next result?
Is there a reason? How is this sum different from just a sum of like T factorial tensors?
I don't see what you mean. Factorial
So
tensor.
like because we're summing over T sub sigma from u to the sigma, but T sub sigma can depend on sigma, right? So why does it matter that we work with sigma per root of sigma? Yeah. Can't we just say we sum T factorial tensors?
Because we're going to take the CB norm of the T sigmas.
But I think maybe I also wondered that, like, could you have put the permutation by sigma into the?
Yeah, that would be much less messy.
No, because that changes the complete dependent norm. That is what Maria's asked before, and is that if you take the CB norm here, then the CB norm of this is not the same as the CB norm of the permuted version.
No, but the idea is that make TP a sum of tensors, of tensors T, whatever. And then on the left, instead of the norm, the CB norm of those T's, we just want those T's capital with sigma inverse. Auto by sigma with that norm.
You can remove the sigma on the right hand side and put it inside the CB norm if you like, but that's just redefining the T sigmas.
But it makes it, I would think, easier to understand because then you would, because the condition on the right would be always to become, always to convert TP into a sum of tensors.
Yeah, maybe that is easier to understand because you can understand more fastly how you decompose your.
Yeah, that's what I meant. But it's a matter of being understandable.
Anything else? Yeah, so it's good that we agree that we don't like this expression. And now that, the first thing that we saw is that this A1's AT can be taken to be the same. Okay, so now the multilinear completely bounded norm is equal to the homogeneous to the polynomial completely bounded norm, and this is somehow nice because now we don't have as many sequence of matrices, which is good. And also for those of you that are familiar with polarization arguments, this somehow says that the polarization constant of the CB norm is 1. You don't lose anything when you take the norm with respect to the polynomial or with respect to the multilinear form. Yeah?
Why can you just say they're gonna argue?
I have to prove that. I mean, it's not difficult, but I think that is going to be difficult to explain. But this, yeah, I can tell you later quickly. Anything else? Okay, so now it comes the moment that everyone is looking for, which is the simplification of the completely bounded norm of the polynomial. And now we forget about this symmetrization thing or whatever the compositions that is difficult to understand. And we just say that the completely bounded norm of a polynomial is the infimum of the completely bounded norms of the tensors that are associated to that polynomial, which is, I think, easier to understand than the previous one. Okay, and I hope that this pushes people to use this method of characterizing quantum query complexity, because now things are a bit more easier to understand.
Why is the completely bounded norm of a tensor easier than that of a polynomial? I mean, you said this is easier to work. You said there's an advantage in this aspect.
No, what I mean is that there is an advantage using this formula. If you don't use this formula and you use this formula, I think that this is.
Oh, you're not saying that this formula has an advantage over the original tensor. You just one more, please. Yeah. So what you're not saying that this formula is easier than the original formula for the CB norm of P.
Yeah, I'm claiming that this is easier, yeah. I mean, here, there were many questions even to understand how you can,
No. He means that you can also take a, I don't know, okay, do you have a polynomial version of the completely bounded norm just for the polynomial without forgetting the tensors?
That's what I meant, yes.
Yeah. So is this easier to think about tensors than whatever my definition was when I forget about the tensors?
That's what I meant, yes.
I don't think there was such a
I don't know.
I don't think
Well,
there.
I know. I know we have a question.
Was there another definition of completely bounded norm of this polynomial without these tensors?
Oh,
So the answer is no.
sorry, all right, so the last line at the moment is the definition.
of course, here you have tensors.
No.
Oh, wait. Well, I think it's fairly normal. I forgot what is the definition of the tensor norm of a CB norm of the polynomial.
Yeah.
What is the definition? That's the definition.
Well, this is not the definition. This is the definition. This is a simplification of the definition.
This expression is the definition of the completely bounded norm of T form, right? The bottom, no, yes, that, right?
No, the bottom one.
Oh, T form, yes. Sorry, yes.
That is the definition, and then you, so that's the definition.
Yes.
And then the red thing that comes next is like, that's nice.
So, I mean, looking at this, is there a reason why this was not the definition? It just seems a bit.
There was a reason, and this because this definition, okay, this does not appear only on this kind of polynomials.
Okay.
So this is a wide, broader theory of the Hagar tensor norms, and this is the norm that works in general for arbitrary things. So the general theory gives you this definition.
Yes. So in this right part, you really mean that P and so that P and T as polynomials are equal over the Boolean Q.
Yes.
So this is something different than saying that you look at all the.
Yeah.
Okay. So you don't look only at all the tensors for symmetrization. It's the first.
Is there, I cannot tell this. I had the impression when you first defined the sort of the tensor of a polynomial that was unique in some way, or maybe I'm wrong.
Well, can you say it louder?
But the tensor of a polynomial is not unique in this sense. It's not.
No. There are many tensors associated to a polynomial, but there is only one that is symmetric.
Oh,
Here,
this
one is a symmetric one. Here is any tensor that is associated to a polynomial. Okay?
Is it somehow, is the symmetric one somehow a good approximation to this infimum, or does it have nothing?
That is something that is kind of an open question. If we can simply say that maybe here we can forget about the infimum and simply say that the completely bounded norm equals to the completely bounded norm of the symmetric tensor. That would be nice because now we can forget about the optimization around the tensors, but that is something that we don't have the simple thing.
Is this calculatable? Like, can you just numerically check it?
Yeah. There is an SGP that gives you this. Yeah. By Sander Griffin and Monilo. So I'm going to talk about this later. So
Noon, maybe we should suppress
questions.
number of questions.
Yeah, only one more slide. Okay, so why these polynomials and these norms are important? These are important because of result of Aaronson and Palazuelos, who stated a full characterization of quantum Fourier algorithms. What they prove is that if you have a quantum Fourier algorithm that does the queries, then the expectation can be extended to one more variable to a 2T form that is completely bounded is completely bounded. Okay, so this is a bit stronger than the polynomial method because it's a full characterization, and it also gives you that the outputs of quantum Fourier algorithms are not only bounded but also completely bounded in this sense that they can be extended to a polynomial that is homogeneous of degree 2T and is completely bounded in this one. Okay, so this is nice because is fundamental, is conceptually interesting to have a perfect characterization of quantum query algorithms. It has been used to prove a few results related to the Aaronson anomalous conjecture. I'm going to talk about that later, but it's a bit complicated to use. Hopefully with this simplification that we have been talking about, is going to be easier to use, but it's also useful for us to simplify the expression of the error PT. I remind you that the error PT is the minimum error that you can make when approximating P using T quantum query algorithms. And we can restate this. This is only saying the same thing, but with another word, as the minimum infinity norm when you take the difference of equally quantum algorithms and the polynomial that you want to approximate. So this is another way of saying what is the error PT, and thanks to the result of Aaronson and Vieta and Palazuelos, this can be simplified, and we can forget about the quantum algorithms and say exactly what is the structure of the outputs. So we can simplify and forget about this expectation of the quantum algorithms and substitute that by completely bounded forms.
Just very stupid question, but in the arrow to the left, I assume, like from your theorem, there needs to be some polynomial there, right? Or the right hand side description, like the arrow to the left, implication to the left, there exists some H such a system. Is that based on something else, or is it just there exists one of these guys? There's a.
I don't know what you.
Never mind. Maybe it's
this is a theorem that is from this wider theory that I was talking about.
I know, but you're plugging it in here, and somehow here it relates to a polynomial, but your polynomial is not the theorem. Which is a polynomial.
Yeah, there exists.
Yes.
It's saying expectation of AX equals H of X comma 1. I think that's what you're saying. That's what it says. There's a TQQA such that its expectation equals X or X. But for giving any H. Okay, never mind.
So now we have this expression for the error PT, which is simpler than just without knowing any structure of quantum query algorithms. Now this is simply a mathematical object that we can analyze. And what we did was simplifying even further this expression for block multilinear 2D forms. I'm not going to read this expression, but believe me that is going to be clear now or in a few slides that this is going to be an easier expression because this we can analyze. So first of all, I want to say what are the elements in this theorem. Block multilinear 2D form is going to be a 2D form that has the following algebraic structure. You take all the variables, you divide the variables in 2D blocks, and in every of the monomials of the expansion of the 2D form, there is going to be one and only one variable of every block. And that means that is a 2D block multilinear form. And V2T that appears here is the space of block multilinear 2D forms. So the error of PT when P is a block multilinear 2D form can be expressed like this. These norms are the dual norms of the completely bounded and the infinity dual and the infinity norm when they are taken with respect to the space V2T. And this is the inner product of the coefficients of P and R. So the next thing is taking the supremum of this error PT when you optimize overall 2T multilinear forms that are bounded in the infinity norm. So by definition of the infinity dual norm, when you take the supremum here among all the P's that are bounded in the infinity norm, then you turn this into the infinity dual norm of R. That is simply the definition of the dual norm. And now this quotient becomes 1. And now we have here in the supremum 1 minus 1 over the quotient of the CB dual and the infinity dual. And remember that the Grothendieck constant kind of link the non-dual versions of this thing. So this is how we are going to be able to analyze this supremum now, because now we have a quotient of completely bounded and infinity norms. They are dual, but there is no problem because we can always use a duality argument and forget about the duals. So we want to specify this result for two cases. The first case is the case of T equal to 1 of one query, and if we take the supremum, what we get is this. But now remember that we are talking about the case T equal to 1, so this is V2, so these are bounded bilinear forms. No, so only bilinear forms, sorry. And in this case, we have the Grothendieck inequality. which we stated the Grothendieck inequality in terms of the completely bounded norm and definite norm of matrices. But believe me that when you are talking about bounded linear forms, the Grothendieck inequality, which can be a bit different, is not different. So the Grothendieck inequality for bounded linear forms, says that the completely bounded norm of a linear form can be ever bounded by a constant times the infinity norm. If we take the dual, which is something that is not difficult to see, that if you have an inequality like this, you can always make the dual version by changing the role of the CB and the infinity norm and then putting the dual, then you get this inequality. So if we rearrange a bit, what we get is that this quotient that appears here can be lower bounded by 1 minus 1 over the Grothendieck constant. And this is an optimal lower bound because of the definition of the Grothendieck constant as the optimal constant. So if we plug this here, we get what we wanted, because now we know that the minimal value of this is 1 over the Grothendieck constant, so the maximum value of this is 1 minus 1 over the Grothendieck constant. And this is what we wanted to do. We wanted to show that there is a characterization of the Grothendieck constant in terms of one query quantum algorithms. Okay, so again, this might open a new road to determine the Grothendieck constant using quantum query algorithms. Any question about this? Good. So the next thing is going to be specifying this result for two queries for t equal to, and now we are going to have the same as before, but now optimizing among block multilinear forms of degree 4. But now we don't have a Grothendieck constant. We have the opposite. We have that the completely bounded norm can be much bigger than the infinity norm. There is a sequence of polynomials such that the quotient of these norms goes to infinity. This can be regarded as a consequence of a work of Jobriet and me that appeared earlier this year, that is based on a work of Briet and Paraforos, where they showed a counterexample to the trilinear Grothendieck inequality. Okay, so we have this, and again, we want the dual version, but that is nothing else than saying that if you have that these norms go to infinity, the dual norms are going to go to 0. And this is exactly what we have here. So this can be as close to 0 as we want, so this can be as close to 1 as we want, which means that we have that the supremum of the error that the error of approximation of bounded polynomials of degree 4 with two quantum queries that are block multilinear is 1, which means that there is no non-trivial additive converse for polynomials of degree 4. So the results of Aaronson and co-authors do not generalize to higher degree. And that is all I wanted to say about the results. I just want to summarize that what we have proved is that there is no converse. Oh, what did I do? It's something will happen. But the results are that we saw that there is no additive converse for polynomials of degree 4, which kind of answers a questions of Aaronson and co-authors. Also, we have characterized the Grothendieck inequality with one query quantum algorithms, and we have simplified the completely bounded norm, which is something nice because now people can understand it a bit better and maybe use it on other problems. So as lines of future work, maybe these polynomials that are hard to approximate with two query quantum algorithms are also hard to approximate with a logarithmic number of queries when this logarithm depends on the number of variables of the polynomials. So maybe this can lead to a way to kind of answer a question that was posted by Aaronson and by Aaronson in a paper of Open Problems last year, where he wondered if you can, for partial functions, attain bigger separations between degree and quantum query complexity than what you can do for total functions. This would not be quantum query complexity of partial functions. It could be like the quantum query complexity of bounded functions, which are not even Boolean, but it might be a way to understand a bit better this question. Also, I want to say that these techniques of completely bounded polynomials characterizing completely quantum query algorithms has already been used in other places. In a work of Nikhil Bansal, Makran Sinha, and Ronald de Wolf that appeared earlier this year, they prove a particular case of the Aaronson and Venice conjecture, which is a conjecture that wonders about if the outputs of quantum query algorithms have an influential variable, and they use this characterization of quantum query algorithms through the completely polynomials to prove a particular case of this conjecture. And as we know that the outputs of quantum Fourier algorithms are not only bounded, but also completely bounded, and the original version of the Aaronson-Manis conjecture was formulated in terms of bounded polynomials, maybe the original version of the Aaronson-Manis conjecture is not true, because the only motivation that we had to believe it is that we have a quantum motivation for it. So maybe what we can also try to do is to disprove the Aaronson-Manis conjecture for bounded polynomials just by taking a family of polynomials that is bounded but not completely bounded, because that family of polynomials does not come out of a quantum Fourier algorithm, so it should not, it might not have to satisfy the Aaronson-Manis conjecture. So that is all I wanted to say. I just want to thank you all for your patience.